Einstein as Unfinished Revolution. The Search for What Lies Beyond the Quantum by Lee Smolin. Is quantum mechanics a complete description of physical reality? Or is it an extraordinarily successful but incomplete theory pointing toward deeper laws of nature?
Oh, wow. Yeah, that is
Right.
that is the question.
So, for this deep dive, we're really getting into the weeds of this. Imagine having like a map that flawlessly predicts the exact location of a city.
Mm-hmm.
But when you travel there, the buildings literally do not exist until the very second you open your eyes to look at them.
Right, which is just...
Crazy, right?
Yeah.
I mean, for nearly a century, physicists have been locked in this fierce debate over whether the city was always there, hidden in the fog.
Yeah.
Or if the sheer act of looking actually built the walls.
And that tension, well, that is the defining crisis of modern physics. What's fascinating here is that we possess this mathematical framework that predicts the outcomes of our experiments with just staggering precision.
Like unprecedented.
Unprecedented precision. The technology that runs our entire modern world is built on it, yet physicists fundamentally disagree on what those equations actually describe in physical reality.
Yeah.
We're dealing with a theory that, works perfectly, but just flat out refuses to explain how the world functions behind the scenes.
Which is exactly why we need to unpack this entire debate today.
Yeah.
I mean, we're going to trace the breakdown of old, reliable classical physics.
Yeah.
And then wade into the absolute strangeness of quantum states and superposition.
Oh, yeah.
We'll confront the measurement problem, which is basically the biggest scandal in science.
Absolutely.
And look at the spooky reality of entanglement.
And we also need to evaluate the wildly different theories attempting to explain all this weirdness. Because physicists have proposed everything from parallel splitting universes to invisible guiding waves.
Right.
And after looking at those, we can examine Lee Smolin's specific arguments for a new way forward, how this all ties into quantum gravity, and, what the latest experiments up through August 2026 are actually revealing.
So hanging over all of this is Albert Einstein. There's this pervasive pop culture myth that Einstein just, grew old, couldn't handle the weird new math.
Yeah, that he was stubborn.
Yeah, exactly. Stubbornly clinging to the past. But looking at the historical record, his objection was, well, entirely different.
It was. He fully accepted the empirical achievements of quantum theory.
Really?
Oh, yeah.
Yeah.
He never denied that the math worked. What he demanded was realism. He believed physics should provide a description of the universe that exists independently of us observers.
Okay.
To Einstein, a theory that stopped at merely calculating probabilities tied to, a specific laboratory setup that was essentially giving up.
Just throwing in the towel.
Right. He believed there had to be a deeper layer of physical reality we simply hadn't discovered yet.
Okay, so to appreciate why Einstein, and now modern physicists like Lee Smolin, are still searching for those deeper laws, we kind of have to look at what we lost. Classical physics, the world of Newton and Maxwell, it made intuitive sense.
It did. I mean, in classical mechanics, a physical state is definite.
Right.
If you look at a baseball flying through the air, you can know its exact position and its momentum simultaneously. You have laws that map that current state to future states with absolute clockwork certainty.
So it's totally predictable.
Exactly. If you resort to using probabilities in classical physics, like flipping a coin,
Yeah.
it's only a reflection of your own ignorance. The coin flip is entirely deterministic. You just, lack the data on the wind speed and the exact force of the thumb.
Right. The universe knows what the coin is going to do. We just don't have the math on hand to figure it out in real time.
Exactly. But at the turn of the 20th century, that beautiful clockwork universe just started to fall apart. Physicists were finding these glaring anomalies that the classical rules just couldn't handle.
Like the black body radiation problem.
Yeah.
Right. The so-called ultraviolet catastrophe.
Yeah, that was a fatal blow to classical reasoning. According to classical physics, an idealized heated object should radiate energy continuously, and that radiation should just keep increasing infinitely at higher and higher frequencies.
Which would mean?
Which would mean every time you turned on an oven, you'd be blasted with infinite lethal radiation.
Which, thankfully, does not happen.
Right. So Max Planck had to introduce a mathematical hack to fix it. He proposed that energy wasn't continuous. It was exchanged in distinct, discontinuous chunks, which he called quanta.
So it's like discovering that water isn't a continuous flow, but a collection of indivisible drops.
Perfect analogy. And Einstein took that idea and ran with it for the photoelectric effect. proving that light itself behaves as localized energy packets, which we now call photons.
Okay, so things are getting chunky, basically.
Yeah, chunky is a good word for it, but it didn't stop there.
Yeah.
The classical framework failed to explain matter itself.
Wait, really? Matter?
Yeah. If you apply classical physics to an atom, the electrons orbiting the nucleus should constantly radiate away their energy, spiral inward, and crash into the nucleus in a fraction of a second.
Oh, wow.
So according to the old rules, solid matter shouldn't even exist. Niels Bohr had to impose quantum conditions to stabilize the atom, which, completely broke classical laws.
Okay, playing devil's advocate for a second here. It feels like we traded a perfectly sensible set of rules for a chaotic, fragmented one. It's like trying to play a modern video game but applying the rules of chess.
Mm-hmm.
The framework just totally breaks down. So why can't we just dig deeper and find a way to patch up naive classical physics? Surely there's a way to explain atoms with, I don't know, classical gears and springs.
Well, the universe actively refuses to let us do that.
Right.
There is no hidden gearwork of simple, naive classical determinism sitting underneath the quantum realm just waiting to be rediscovered.
It's just not there.
It's not there. As we'll see when we get to Bell's theorem, modern experiments completely rule out a return to local classical physics. Whatever the successor to quantum mechanics looks like, it has to reproduce all the bizarre quantum successes we observe. We cannot go backward.
Okay, let's unpack this. If the definite classical states are permanently thrown out the window, what replaces them?
The quantum state.
Right, and this is where the language gets notoriously slippery.
Slippery is a very good word for it. The quantum state doesn't give you a list of definite properties. Doesn't say, the electron is exactly here, moving at this exact speed.
Yeah.
Instead, it encodes amplitudes for various possible outcomes relative to a specific measurement. These amplitudes are complex numbers, meaning they have a mathematical phase, and they can combine, overlap, and interfere with each other. This is what we mean by superposition.
Okay, wait, I want to pause right here because we need to kill a very common misconception.
Please do.
When pop science articles talk about superposition, they almost always say, oh, the particle is in two places at once. They treat superposition like some, I don't know, mythological shapeshifter.
Yeah.
Literally existing as a split physical object.
Yes.
But superposition isn't a physical spreading out, is it? It's mathematical coherence.
Exactly. It is mathematical and physical coherence. It describes a potential, not a classical object, occupying multiple physical locations simultaneously.
Right.
To get from those overlapping, interfering amplitudes to a real outcome we can see in the lab, we use something called the Born rule.
The Born rule.
Yes, the Born rule tells us to square those amplitudes, which strips away the complex phase and leaves us with a standard probability of finding a specific outcome.
But the interference part, before you apply the Born rule, that is vital to understand. That's a famous double slit experiment, right?
It's the one.
So you fire individual particles, one by one, at a barrier with two slits. If they were classical bullets, you'd get two piles behind the slits.
Just two simple piles?
But instead, the probability amplitudes for going through each slit interfere with each other, building up a pattern on the back wall that looks exactly like overlapping ripples of water.
Yeah, and the crucial detail there is how fragile that interference pattern is. Because if you set up a detector at the slits to acquire which path information.
Meaning you try to measure which slit the single particle actually went through?
Right. If you look, the interference pattern vanishes instantly. You just get the two classical piles.
Wow.
The sheer act of extracting information changes the available outcomes, which leads us straight into three massive concepts: uncertainty, complementarity, and contextuality.
Okay, let's start with uncertainty, because people misinterpret the Heisenberg uncertainty principle all the time. The common thought is just that our microscopes are too clumsy, so when we try to look at an electron, we accidentally bump it and change its speed.
Yeah, that implies the electron actually had a definite position and speed before we bumped it, which is false. Entirely false. Uncertainty is a fundamental limit built into the architecture of reality. Let me give you a very mundane analogy. Think about baking.
Baking.
Mixing the batter and baking the cake are non-commuting actions. If you mix the ingredients and then bake them, you get a cake.
I say, yeah.
But if you put unmixed flour and eggs in the oven to bake and then try to mix them afterward, you get a burnt mess.
It's a terrible mess, yeah.
Right. The order of operations fundamentally changes the reality of the outcome.
So in quantum math, measuring position and measuring momentum are like baking and mixing. The order matters, which means mathematically they cannot both be sharply defined at the exact same time.
Precisely the right way to think about it. The MAC prevents them from having simultaneous sharp values. And this ties into Niels Bohr's concept of complementarity.
Right.
He argued that mutually exclusive experimental arrangements like setting up a lab to measure a wave versus setting up a lab to measure a particle, they reveal different aspects of the system that simply cannot be combined into one single classical picture.
And contextuality pushes that even further. It means the value you measure for a property inherently depends on the context of the other measurements you're making at the same time. You can't assume the particle was just sitting there with a pre-existing value hidden in its back pocket.
No, you can't. And with all this conceptual weirdness, we have to be absolutely clear on a point of scientific fact here. Despite these deeply counterintuitive features, quantum mechanics has not been experimentally disproved.
Wait, not at all.
Not at all. It remains an extraordinarily successful predictive framework. The entire standard model of particle physics and all our advanced electronics rely on these exact principles being perfectly correct in their predictions.
So the equations work flawlessly. It's the meaning of the equations that Lee Smolin is targeting. He is frustrated that we don't know what is actually happening.
And Smolin is incredibly disciplined about this. He insists we apply a strict explanatory audit to every quantum claim. You have to clearly separate 4 distinct questions. 1, what was physically prepared in the lab? 2, what specific quantity was measured? 3, what statistical pattern was observed? And finally, 4, what assumptions are you using to connect those statistics to a grand claim about the nature of reality?
See, I love that audit because it stops physicists from smuggling their own philosophical beliefs into the raw data.
Exactly.
And we desperately need that discipline when we hit the biggest roadblock in the entire field, the measurement problem. We've been talking about these smooth overlapping amplitudes, but when I look at a Geiger counter or a computer screen, I only ever see one definite classical outcome. I never see a superposition. Why?
You've just identified the structural tension at the heart of textbook quantum mechanics. The theory operates on 2 completely contradictory rules.
Contradictory.
Yeah. Rule 1 governs the system when it's left alone. It evolves smoothly, predictably, exploring all those amplitudes. But Rule 2 kicks in the moment a measurement happens. The smooth evolution violently stops, and the state suddenly collapses into one definite outcome.
Okay, but what physically qualifies as a measurement?
That is the problem. The boundary between Rule 1 and Rule 2 is conceptually opaque.
Wait, I thought Schrodinger's cat was a real experiment proving that things can be in 2 states at once. Wasn't he saying a cat can actually be dead and alive?
Oh, that is a brilliant piece of historical irony. Erwin Schrödinger didn't propose that thought experiment to prove quantum mechanics.
He didn't.
No, he proposed it to mock the measurement problem. He was pointing out a flaw.
Oh, wow.
He essentially said, if we assume the microscopic rules apply smoothly to the macroscopic world, then a radioactive atom in a superposition of decaying and not decaying will entangle with a poison release mechanism, which entangles with a cat.
Right.
You end up with a cat in a superposition of alive and dead. That is obviously absurd. So where in that chain does the superposition actually stop?
So he was using the absurdity to demand an answer for how we get definite macroscopic outcomes.
Exactly. Now, a lot of modern physicists point to decoherence as the answer to this. The idea is that a quantum system doesn't exist in a vacuum. Let's use an analogy.
Okay.
Imagine trying to listen to someone whispering a secret in an empty, quiet room. You hear the information perfectly. That's a coherent quantum state.
Got it.
But then you move that conversation into a crowded, noisy concert hall. The whisper is still happening, the sound waves are still there, but they immediately get hopelessly scrambled by the noise of 1,000 other conversations. The music, the air conditioning, the environment interacts with the system.
So in physics, stray photons, heat, air molecules, they're the noisy concert hall. They constantly bump into the quantum system.
Yes. This environmental entanglement rapidly causes the system to lose observable phase coherence. The delicate interference pattern washes out, and the system begins to look classical. Decoherence is a real, measurable phenomenon.
But we need to correct a massive assumption here. Decoherence explains why the interference disappears, why we don't see macroscopic superpositions. But it does not by itself universally settle why one unique outcome actually occurs. It explains why the menu of reality looks classical, but it doesn't explain the mechanism that chooses what we actually get for dinner.
A vital distinction. The reduced state resembles a classical statistical mixture, but without adding new philosophical interpretations, decoherence alone doesn't select the actual event.
Okay.
And while we are clearing away the brush, let us address another major piece of pop science mythology. A conscious human observer is not required for ordinary quantum measurements.
Thank goodness you brought this up. It is wild how fast this gets mystical. You see entire books claiming that human consciousness literally creates reality by collapsing wave functions.
Yeah, and those claims go far, far beyond any established scientific evidence. Detectors, amplifiers, and the thermal environment do the job of measuring perfectly well. Irreversible physical records are created independently of whether a human mind is paying attention.
Okay, so the measurement problem is agonizing enough with just one particle, but it scales up into something almost terrifying when two particles interact and then separate. Let's talk about entanglement.
Oh, entanglement. It occurs when two or more particles share a joint state that simply cannot be mathematically reduced to independent individual parts. If you separate these particles even by light years, measurements performed on them will reveal structured correlations that defy any classical explanation.
And this brings us back to Einstein. In 1935, along with Podolsky and Rosen, he published the famous EPR paper to challenge the idea that quantum mechanics was a complete theory.
Right, and their argument was brilliant in its logic. They relied on locality, the principle from relativity that nothing, no signal or influence can travel faster than light.
Right.
They reasoned that if making a choice about how to measure particle A on Earth cannot instantaneously alter the physical reality of particle B on Mars, then the correlations we observe must mean the particles had predetermined properties all along.
Like they planned it.
Exactly. The particles must have left the source with a shared plan. Therefore, since quantum mechanics only gives probabilities and doesn't describe this shared plan, the theory must be incomplete.
They were essentially arguing that the particles have a hidden manual they are reading from, and quantum mechanics is just too blunt of an instrument to read the manual.
Precisely. And this debate stayed purely philosophical for decades. But then, in 1964, a physicist named John Bell did something practically miraculous. He turned this philosophical debate into testable math.
Okay, we need to ground this, because mathematical limits of correlation is pretty dense. Let's use a police interrogation analogy.
Good idea.
Imagine two criminal suspects who were arrested and placed in separate, soundproof interrogation rooms.
Right, so they can't communicate. The police ask them a series of unpredictable, randomized questions. If the suspects are relying on a predetermined alibi, a hidden variable, a plan they made before getting arrested, there is a logical limit to how often their answers will perfectly align, given they don't know what questions the other's being asked. That limit is Bell's inequality.
But if they had magical walkie-talkies in their heads and could instantly hear what the other was being asked, they could perfectly coordinate their lies every single time, breaking that limit.
And when experimental physicists actually set up these tests with entangled photons, they found that quantum systems routinely break Bell's limit.
Wow.
The 2022 Nobel Prize in Physics was awarded specifically for modern loophole-free Bell tests that prove this. The universe violates Bell inequalities. The particles do not have a pre-agreed classical alibi.
So Einstein was wrong about the hidden manual. But before people start thinking this means we have magical walkie-talkies, we need to correct another huge misconception. Bell test violations do not permit faster-than-light communication.
Right, we call this the no signaling principle. Even though the correlation between the particles defies local classical limits, the individual outcomes you observe on Earth are still completely random. You can't control whether you get a spin-up or a spin-down result. Because you can't control the outcome, you can't encode a message into it. To actually verify the correlation with the observer on Mars, you still have to send a regular light-speed text message to compare notes.
So non-local correlation is not a usable superluminal telegraph.
Exactly. Non-local correlation is not communication.
And there is one more misconception to clear up here. Bell experiments do not uniquely prove one specific interpretation of quantum mechanics. They only exclude local hidden variable accounts. They definitively tell us what the universe isn't, but they don't confirm what it is.
And that leaves physics in a remarkable predicament. Experiments rule out simple local realism. The mathematical equations work beautifully, but the math refuses to provide a clear picture of what is happening behind the scenes.
So how do we proceed?
Well, this is why physicists have developed a menu of wildly different interpretations that all use the exact same math but describe entirely different versions of reality.
Here's where it gets really interesting. You have some of the most brilliant minds in history looking at the exact same whiteboard, agreeing on all the predictive numbers, and walking away with fundamentally incompatible views of what the universe is.
It's wild.
Let's explore this menu. We have to start with the Copenhagen family. which has been the default pragmatic approach for decades.
Yeah, I say family because Copenhagen isn't a single strict doctrine. It's a collection of related views. Broadly, it focuses heavily on the classical descriptions of the experimental arrangements. It treats the boundary, the cut between the quantum system being measured and the classical instrument doing the measuring, as flexible and instrumental.
It's often summarized as, shut up and calculate, right?
Yeah.
It essentially says the math gives us the probabilities of what the macroscopic instruments will show. Asking what the particle is doing when we aren't looking is a meaningless, unscientific question.
And for pragmatic engineers building lasers or microchips, that approach is entirely sufficient. But for a realist like Lee Smolin, it is deeply unsatisfying. If you believe physics should describe a reality independent of human lab equipment, you might turn to pilot wave theory.
Okay, how does pilot wave explain things?
It's often associated with de Broglie and Bohm. Pilot wave offers a completely clear, deterministic, realist account. It argues that the quantum wave function is real, but it also says actual definite particles are real too.
Okay.
The particles have exact trajectories at all times, and they are guided by the wave function. It eliminates the measurement problem entirely. There is no collapse, just particles moving along guided paths.
That sounds perfect. It gives us back our definite reality. What's the catch?
The cost is severe. To explain those Bell test correlations we talked about, the guiding wave dynamics must be explicitly physically non-local. An event or measurement happening here must instantaneously affect the guiding wave everywhere in the universe at once.
Oh, wow. Everywhere at once.
Yeah, and that extreme non-locality makes it notoriously difficult, if not impossible, to reconcile with Einstein's special relativity, which treats space and time as a unified fabric with strict speed limits.
So if we hate the idea of instant universal non-locality, and we hate the mysterious measurement collapse from Copenhagen, we are forced to look at the many worlds interpretation, or aberration quantum mechanics.
Right. Many worlds takes the math of quantum mechanics absolutely literally. It says, Rule 1, the smooth, unitary evolution of superpositions is all there is. There is no Rule 2.
No collapse.
The wave function never collapses. Instead, when a quantum system in a superposition interacts with a macroscopic environment, the universe itself branches.
So if a particle can go left or right, it goes left in one universe and right in another.
Essentially, yes. The decohered components of the wave function become separate, non-interacting branches of reality. Everything that has a quantum probability of happening does actually happen in some branch of the multiverse.
But wait, if that is true, how does probability even exist? I mean, if I have a 20% chance of getting a specific result, how does that make sense if I know for a fact that it is 100% guaranteed to happen to some version of me in a branching universe?
You've hit on the major vulnerability of many worlds. Explaining how the Born rule probabilities emerge in a deterministic, branching multiverse is a massive challenge.
Right.
Proponents often use complex decision theory or typicality arguments to solve it, but it remains heavily debated. We also need to correct a very pervasive cultural misunderstanding here.
Oh, yes, please.
The existence of quantum computers does not prove the physical existence of many worlds.
Thank you. It is so common to read tech articles claiming that a quantum computer works by splitting the universe, running the calculations in parallel realities, and then bringing the answer back to our timeline.
Yeah, that is a fun science fiction metaphor, but scientifically, it's unfounded. Standard experiments that confirm unitary quantum predictions, which is what a quantum computer relies on, do not uniquely confirm many worlds over empirically equivalent rivals like pilot wave.
Okay, let's pivot to another option on the menu. Objective collapse models, like GRW or CSL. These are fascinating because they don't just interpret the math, they actually alter the Schrödinger equation itself.
Right. They propose a physical mechanism for collapse. They suggest that superpositions spontaneously localize on their own, completely randomly, without needing any measurement or environment.
Okay, so it just happens.
Yeah, for a single particle, this spontaneous collapse might happen once every 100 million years. But if you have a macroscopic object made of trillions of particles, the mathematical probabilities stack up, guaranteeing that the object collapses into a definite state almost instantaneously.
The scientific beauty of this approach is that because they alter the math, they're actually falsifiable. They predict a very slight, continuous amount of noise or thermal radiation as a byproduct of these spontaneous collapses. We haven't detected that specific noise yet, but we are actively building experiments to look for it.
And finally, we should mention the informational, relational, and cubism approaches. These dive deep into epistemic philosophy. Relational quantum mechanics suggests that properties of a system only exist relative to the physical interactions it has with other systems.
Right, so it's all relative.
Yeah, and cubism goes further, arguing that the wave function isn't a physical thing out in the world at all. It merely represents an agent's personal, subjective probability assignments about what they expect to experience.
This usually brings up the Wigner's friend thought experiments, right? Where you have an observer inside a lab measuring a particle and another observer outside the lab measuring the whole room. They can arrive at contradictory yet mathematically valid facts about the same event.
Exactly. But Lee Smolin is highly critical of these epistemic views for a very specific reason:
Which is?
cosmology. He argues that if you treat quantum mechanics merely as a tool for an agent's knowledge, the theory fails to describe the universe as a whole. The universe doesn't have an external agent or a macroscopic apparatus sitting outside of it to look at it.
That makes total sense. How did the early universe evolve for billions of years before there were any agents around to assign probabilities to it?
Right, which perfectly sets up Lee Smolin's own specific argument. He looks at this wildly contradictory menu: multiple branching universes, invisible non-local guiding waves, spontaneous math alterations, personal subjective knowledge, and he concludes that none of these can be the final answer.
So what's his solution?
He argues we need a fundamentally new, realist direction. He introduces a concept called the real ensemble proposal.
Okay, the real ensemble proposal, how does that work?
Smolin's real ensemble idea attempts to explain where quantum probabilities come from without relying on abstract mathematical spaces. He proposes they arise from physical relations among similar systems distributed across the entire universe. It relies on the concept of precedence in nature.
Precedence.
Yeah.
Like in a court of law.
Exactly like that. Common law is based on precedent, how similar cases were decided in the past. Smolin suggests that when a novel quantum event occurs, its behavior might not be governed by timeless mathematical laws sitting outside the universe. Instead, its behavior is shaped by how similar physical systems have behaved in the past, anywhere in the cosmos.
Wow, that is a deeply provocative idea. It suggests that the laws of physics might not be eternal and fixed, but that they might actually evolve.
Yes.
But we must be careful to frame this properly for the listener. This is highly speculative, completely outside of standard textbook quantum mechanics. We need to squash a potential misconception right here. Lee Smolin has not completed Einstein's unfinished revolution.
That is absolutely correct. Smolina's ideas are a provocative minority research direction, not a finished consensus replacement theory. The hurdles for his real ensemble proposal, or frankly any new theory aiming to replace quantum mechanics, are incredibly steep.
Yeah.
You can't just explain a single particle in a box. A new theory must fully recover quantum field theory, standard particle physics, and relativity.
And it has to explain the quantum vacuum, right? Because the vacuum isn't just empty nothingness.
Not at all. The quantum vacuum is a lowest energy state teeming with complex structure, fluctuations, and correlations. Any new theory must account for that structure while also maintaining the rigid causal framework of special relativity, known as Lorentz invariance, and somehow accommodating the proven non-locality of Bell tests.
It is a monumental task.
It is.
If we connect this to the bigger picture, Smolin's ultimate point is that physics is currently treating these massive problems in isolation, which might be exactly why we are stuck.
Yes. Smolin forcefully argues that the foundational problems of quantum mechanics and the quest for quantum gravity are essentially two sides of the same coin. Think about it. General relativity, Einstein's theory of gravity, describes a dynamical, flexible space-time where the geometry bends and responds to matter.
Right.
But quantum theory relies on a fixed, rigid background stage and an external ticking clock of a time parameter. The two theories speak fundamentally incompatible languages.
This is the infamous problem of time in physics.
Yes. In many attempts at canonical quantum gravity, the time variable actually drops out of the mathematical equations entirely. Explaining our lived experience of change and causal order becomes a massive theoretical hurdle. Smolin spent years helping to develop loop quantum gravity, which attempts to quantize space itself in a way that doesn't require a fixed background.
Right.
But his current stance is that to truly solve quantum gravity, we cannot ignore the quantum measurement problem. We have to solve them simultaneously by finding a realist account that describes the entire universe from the inside out.
So where does this leave the scientific community right now? Let's bring this up to date with the modern landscape through August 2026. Because this isn't just a debate for philosophers in tweed jackets arguing at blackboards anymore. We are actively testing these boundaries in the lab.
Oh, absolutely.
Right.
We are operating in the middle of an incredible technology foundations loop. The massive global push to build quantum computers, quantum networks, and error-corrected qubits is unintentionally creating unprecedented, pristine experimental platforms to test these foundational principles.
We are pushing the limits of superposition. Physicists are performing matter-wave interferometry with increasingly massive, complex molecules, trying to see just how large a physical system can get and still maintain a quantum superposition before it behaves classically.
They are actively hunting for that boundary. If an objective collapse model is correct, these large-scale superposition tests will eventually hit a hard physical wall where coherence is destroyed spontaneously, even if the environment is perfectly shielded. So far, experiments are placing tighter and tighter bounds on those collapse models, pushing the limit higher.
There's also cutting-edge theoretical and experimental work proposing ways to test if gravity itself can entangle quantum systems.
Which would be revolutionary. If an experiment can show that the gravitational field can mediate entanglement between two masses, it strongly implies that gravity itself must have quantum features, bridging that gap between relativity and quantum mechanics.
But despite all this incredible technology, as of August 2026, there is still absolutely no consensus interpretation of quantum mechanics.
Sociologically speaking, the pragmatic Copenhagen-style approach still dominates most university physics departments, mostly because it works perfectly well for day-to-day calculations. If you are engineering a semiconductor, you don't need to worry about multiple universes.
They do dominate sociologically. But sociological preference is not scientific proof.
Exactly. The field is far more experimentally connected than it was in Einstein's era. But the clear smoking gun experimental difference needed to discriminate between these interpretations to definitively prove many worlds over pilot wave or relational over objective collapse remains entirely elusive.
So what does this all mean? We started this deep dive by asking if quantum mechanics is a complete description of physical reality, or if it points to deeper undiscovered laws. Let's synthesize everything we've explored.
Well, what is absolutely scientifically secure is that quantum mechanics and quantum field theory are extraordinarily successful frameworks. The phenomena of entanglement, contextuality, and Bell violations are non-negotiable facts of nature. Any deeper successor theory must flawlessly reproduce them. However, what remains profoundly unresolved is the origin of unique, definite outcomes, the correct fundamental ontology of the world, and how to integrate this quantum behavior with the dynamical spacetime of gravity. The fact that the same predictive equations permit multiple, vastly different interpretations proves that the conceptual foundations are not settled.
Smolin's vital contribution is insisting that realism remains a legitimate, necessary scientific goal. We shouldn't throw our hands up and say, well, nature is fundamentally unknowable just because our current mathematical tools are statistical. Quantum mechanics may very well be incomplete, but the existing evidence doesn't conclusively establish exactly what that missing physics looks like yet.
And the conceptual tensions demand open, mathematically rigorous, and experiment-constrained inquiry. The physics community is actively looking for the exact physical differences that would distinguish mere philosophical interpretation from actual physical description.
The map we have is undeniably brilliant at getting us to our technological destinations. But we are still arguing in the dark about what the terrain actually looks like under our feet. And that is exactly why the revolution remains unfinished. This has been an independent COSMORA HQ book overview in audio podcast format. It is not an audiobook narration, adaptation, abridgment, reconstruction, authorized production, or substitute for Lee Smolin's original work. We encourage you to access the book legally to explore Lee Smolin's complete argument. Do quantum mechanics' unresolved conceptual problems indicate missing physics, or do they reveal the limits of human intuition about reality?